Hey guys, welcome. So today we're going to talk about rational expressions. We're going to just pick up with where we last left off in class. We had just gotten to, but we didn't get to actually do anything yet with multiplying rational expressions. So that's what we're going to do next. So before we do some examples, I just want to refresh a couple of rules for you. So the first one that I want you to remember is this one here, which essentially says that if you have the nth root of something to the m power, you can write that in its exponential form as x to the m over n. So that's going to be one important rule that we want to remember. Another important rule that we have is you can look at, for example, this next one here. And that says that if you have any two numbers with the same base and you're multiplying together, you add those exponents. And then finally, the other rule that will be important here is, of course, the sort of separation rule. So that says that if you have two numbers underneath any kind of root, doesn't have to be a square root, can be a third root, fifth root, whatever. But the idea there is that you can separate them using just sort of separation. You can say the nth root of the product is the product of each of the nth roots. All right, so let's do some examples that will sort of showcase how we can do that. All right, so the first thing that you want to do in these type of examples, all right, so first thing is to separate. Right. So what I mean by that is, in this case, the first thing that we would want to do is we would want to say, okay, well, my 3x to the fifth square root, I want to write that as square root of 3 times square root of x to the fifth. Right. And then, of course, similarly with the other one, we can write square root of 6x to the fourth as square root of 6 times square root of x to the fourth. All right, so that's the first step. Now, the next thing that you want to do is you want to group each type of term now together. So you want to group each type of term in its own radical. Okay, so what I mean by that, for example, is that I want to take, see, did I use red? Yeah, so let's maybe use a different color. Let's use green. So for example, I can take this square root of 3, this square root of 6, and I want to put them together inside their own radical using the same rule that we actually used to undo them, but now we're going to bring these two specifically together as a square root of 18. Okay, and then similarly, we're going to do a similar thing here with square root of x to the fifth and square root of x to the fourth, and we're going to put them together as x to the fifth times x to the fourth, of course, would be x to the ninth, right? I'm sort of skipping steps there, but sort of where is that coming from? That's coming from, well, these two would be square root of x to the fifth times square root of x to the fourth. And then I shouldn't use an arrow here. I really should use an arrow this way. But then, of course, you're multiplying two numbers with the same base. You add their exponents, so 5 and 4 would give you 9. All right, and now the last thing that you need to do here, almost done, is now you just simplify each expression. And this is something that we already did in class. So, of course, we'll sort of talk about the individual steps as we go. But the idea here is for your number terms, what do we do there again? Well, for that, so for example, for the square root of 18, anytime you have numerical terms, you want to try and write that as a product of two numbers, one of which is a perfect power of the type of root that you're taking, right? So in this case, we have a square root. So we would like to write it as a perfect square times something else. So of course, if you think about it for a little bit, you can think of 18 as 9 and 2, and this is good because 9, of course, is a perfect square, right? So, of course, you can write that as a 3 times the square root of 2. Okay, and then we can take our variable terms and we can convert that to its exponential power, or exponential form, I should say, and this would be a 9 over 2, right? Because if you don't see the number there, there's no number there, so we assume that it's a 2, and then of course that's 9 over 2. If we write that as a mixed number, that's x to the, how many times is 2 going to 9? It goes in 4 times. Of course, there's 1 left over, so we can write that as x to the 4th times x to the 1/2, right? And of course, if we want to take out one more time, you could say if this is x to the 4th square root of x. Okay, so now we're almost done. The last thing that we really need to do here, and if I said it was the last thing before, I lied, but the last thing that we need to do is now just group stuff outside together. And then everything that's underneath a square root will go under one square root, right? So group stuff inside together. All right, so probably not the most mathematically rigorous way to say that, but that's the idea. All right, so now we're combining these two things. And if we do that, we have a 3 and an x to the 4th on the outside, so that will just become a 3x to the 4th. What do we have inside of square roots? We have a 2 and an x, so together that will become a square root of 2x. All right, so that's the first example. All right, now if you understand that pretty well, all right, maybe now would be a good time to pause the video and then you could try the next one on your own. All right, but assuming you're pausing when you want to, we're just going to go ahead and we're going to do it. If you'd like to try it on your own, of course, pause it, and then once you're done, you can try it, with me. But let's get right into it. All right, so for this example, same idea. First thing we want to do is separate. I'm not going to write out the steps each time, but just will indicate what we're doing here. So first, I want to write this. First one we'll write as cube root of 3 times the cube root of x squared. And then the next one I'll write as a cube root of 9 times the cube root of x to the 4th. All right, so now we're going to put each one of these together inside its own group here. So we'll group our numerical terms together. So we have, let's use a different color. So we have the cube root of 3 and the cube root of 9. So we'll make them together. 9 times 3, of course, would give you a 27. So that would be a cube root of 27. All right, we'll come back to that. If you're like me, that makes you excited because we can simplify that very nicely. But anyway, now we'll look at our variable terms, and then that'll give us a cube root of x squared times x to the 4th. So of course, that's going to give you an x to the 6. All right, so now we'll simplify each. Now, of course, we just said a minute ago that the cube root of 27 is a perfect cube. So that will give you a 3, right? If you do 3 times 3 times 3, that'll give you 27, and that's what we want. All right. Now for the square root, sorry, not the square root, the cube root of x to the 6, we can write that in its exponential form as 6 over 3. So of course we can write this whole thing as a 3, and then 6 over 3 we can write as x squared. Now in this case there's no root terms, so we're actually done, right? Because the only thing that's left is this 3x squared. So our final answer is just 3x squared. All right, so that one's not too bad. All right, so hopefully this isn't too difficult. So let's try one where we have a couple more terms here. All right, so this one will probably get a little messier, but nothing we can't handle. All right, so let's do it. All right, so as per usual, first thing, let's try orange. First thing we'll do first is we'll separate all this. So we got a 5th root of 4, 5th root of x to the 9th, fifth root of y squared. And then in the other one, you got a fifth root of 16, fifth root of x squared, and a fifth root of y to the 21st. All right, and again, this looks a lot more gross than the last one because we have so many more, well, you have two more terms at this point, but it's really the same process. We just have to do it for one extra variable. So we look at our two numerical terms. I guess this is part of step 2, right? So then 16 and a 4 will give us a 64. If we look at our x terms, those colors look similar, but hopefully you get the idea. We have a fifth root of that will become 9, and 2 would give us x to the 11th. And let's see, sure, green. Fifth root of y squared, fifth root of y to the 21st. That gives us a fifth root of y to the 23rd. So now we just have to work on each of these. Now for fifth root of 64, right, we need a number that if we multiply by itself 5 times give us 64. But if you think about it, there's no number that does that. So we're going to need a number that divides it that's a perfect fifth power, right? And in fact, you don't have to look too far because first couple fifth powers, of course, 1, but that doesn't do us any good. But then if you look at 2 to the 5th, 2 times 2 times 2 times 2 times 2, that gives you a 32. And that's going to be the number that we want, right? So 32 divides 64. So now we can come back over here and we can write that as a fifth root of 32 times a fifth root of 2. So of course we can write that as a 2. We just saw that over here times a fifth root of 2. All right, now let's move on to the x term. So if we do that, that's an x to the 11 over 5. So again, how many times is 5 go into 11? It's going to go in twice with 1 left over. So of course we can write that as x squared times fifth root of x. And then for fifth root of y to the 23rd, we can write that as 23 over 5. How many times does 5 go into 23? Goes in 4 times with 3 left over. So we can write that as a y to the 4th, fifth root of y to the 3rd. All right, so now all that's left to do is now we just have to combine everything. So we need to combine this, this, and this. So if we look at all of our numbers on the outside, we have a 2, we have an x squared, and a y to the 4th. And then our numbers on the inside, we have a 2, we have an x, and we have a y to the 3rd. I should put a fifth root in there. Let's maybe try and do a little better there. Oh, all right, well, whatever. So then if we do this, we should get a fifth root, there we go, of 2xy to the 3rd, and that's our final answer. All right, so again, not too much different from example to example once you get the hang of it. So we're going to do a couple more examples that are enlightening, and then we will stop this video, and that will be it for multiplying rational expressions. But just as a couple more examples, let's go ahead and do it. So now this one sort of combines some old stuff, as you see here, that we have a distributive property. Right, we want to take square root of 3x, we want to multiply it by square root of 27x, and we want to take square root of 3x and we want to multiply it by 12, right? So now, of course, here, what we're really doing is almost two separate problems, right? If we sort of break this into what we just did a second ago, I essentially have square root of 3x times square root of 27x as one problem, minus square root of 3x times square root of 12, right? Now, of course, at this point, you have two options. So one option is that you can simplify and then multiply And of course, the other is to multiply then simplify. All right, and it doesn't really matter. In certain scenarios, it works out better, to simplify first, so that way that your numbers don't get too large. But I think in this case, we should be fine just multiplying first and then simplifying. If you get to a problem where you see that the numbers are really large, then it's probably a little bit better um, to simplify first and then multiply. But in here, it's not that bad, right? So for this first part, again, we have square root of something times square root of something. So we could say that's square root. And I'll maybe write this out a little bit better since this is slightly different, right? So we want to think of this as square root of both of those two things multiplied together. And similarly for this one, that will be a square root of a 3x times 12. Right? So now if we look at this one a little more closely, so 3 times a 27, I believe, should give you an 81, right? Which is good. And then of course, x times x is x squared. And then the other one, 3 times 12 will give us a 36. And then we have an x, right? So of course, I guess I should be saying these are all equal, right? Okay, so then this equals, we can say 81 and x squared are separate. All right, but those are both perfect squares, so that's not bad. Then we have square root of 36, square root of x. So now we just simplify all of our square roots. Square root of 81 is 9, square root of x squared is x, square root of 36 is a 6, and then square root of x, unfortunately, is just going to stay square root of x, and that's it as far as that one goes. All right, so that one, again, hopefully not too bad. So that one's fine. Now, example 7 is not particularly hard, but I do want you to notice that we have sort of a familiar formula going on, right? And if you don't see that right away, you can see that this is, let's see, maybe kind of zoom out a little bit, sure. So maybe notice here that you have, let's put it this way, so you have something in the form of a plus b, and then the same thing except with a minus sign. And this, of course, is your difference of squares, difference of two squares formula. So what does this come out to be? This is, of course, is a squared minus b squared, right? So I'll show it both ways. But the idea here is that if you were to FOIL this, square root of m times square root of m is square root of m squared. And then we get a minus square root of m times n. And then we get a plus a square root of n times m. And then we get a minus square root of n squared. All right. Now, of course, if you look at these two middle terms, right, even though the order is different, right, we could say that this term is just a square root of mn. Maybe zoom in a little more. So that's a square root of mn, and this one's positive, and the other one is negative. So they're just going to cancel each other out. So now what we have left, square root of m squared, well, that's just m. And then minus from this minus over here, and then square root of n squared is just n. Right? So this is actually going to showcase a property that we're going to use a little bit later on in this section when we have to talk about dividing with radical expressions and what's known as rationalizing a denominator. All right, so there's one more example. There's two parts that we're going to look at, and then that will wrap up our multiplying with radicals. All right, so this first example we can do quickly, right? Oh, and I guess I forgot to mention that in this last example, we could have also seen that it's in this form, and then we have a square root of m squared minus square root of n squared, right? But this is going to give you the same thing is that. So if you recognize that it was in that form, you could probably do this a little more quickly, but either way, you should get the same answer. Okay, back to example 11. So one way you can think of this, of course, is that this is square root of x plus 4 times x plus 4. And of course, that's a square root of x plus 4 squared, right? Now, in this case, you can think of it as the square root and the square undoing each other. And of course, this would give you an absolute value of x plus 4. Now, if you didn't put the absolute value, you know, technically it needs to be there. But in most contexts, we assume that this won't be ill-posed. So if you said x plus 4, like on a quiz or a test, in most cases that's fine. But there is that caveat there that if this x plus 4, if that were negative, then you would need the absolute value there, right? Because you can't square something and take its square root and then have a negative number. All right. But anyway, so either one of these two answers would likely be fine, but if you want to be sort of the varsity correct answer, that's the preferred. And let's see, I think that's how you spell it. That's why I teach math and non-English, but anyway. Okay, so last example that we'll look at is the square root of 2x squared minus 24x plus 72. All right, now if we think about this, the only way that we could really simplify this is if all this stuff worked out to be a perfect square. So we want a perfect square here. All right, so the only hope what we have of doing that, we have a trinomial. So the only hope we have of getting a perfect square is if we factor this. So we need the factor. All right, so if we factor this, we could take a 2 out of everything. And then what do we have left? We have x squared minus 12x, and then plus a 36. And of course, if we think about if we can factor it, we can maybe factor it this way. So we need two numbers that multiply to 36 and add to a negative 12. And luckily, those two numbers are the same. They would both be a minus 6. So we can write this as a square root of 2 times an x minus 6 squared. So last but not least, we can write this as square root of 2 times square root of x minus 6 squared. And then, of course, same idea, square root of 2, of course, is just going to come down. But here, if you want the varsity answer, you would want an absolute x minus 6. But if we are assuming that x minus 6 is positive, or I guess non-negative would be the better way to put it, then you could just say that it's a square root of 2 times x minus 6 in just parentheses, right? So either one of these answers is probably okay, but again, this one would be sort of the more general answer. Let's put it that way, more general. Okay, but that wraps this video up for multiplying radical expressions. So I will see you next time, and we will be talking about dividing rational expressions.